Let's consider for a second an object that we have lifted up above the ground. Let's say, just give a number to it, maybe it's 2 meters up above the ground. And we consider our system to include the ground, include the earth maybe. And as we lift this object up, we had to do work to lift it up there, so we had to give it some type of energy in order to get it up there. That was external, us coming in and lifting it up. Then we let go. Well, we know that as we hit the ground, we're going to have some velocity equal to something, and we could calculate that with some of our kinematic equations if we wanted to. So that means that down here it has some amount of kinetic energy. Well, where did that kinetic energy come from? Might be a good question. It turns out we do have energy up at this location, and we call it our gravitational potential energy. I like to abbreviate it potential energy of gravity. And that potential energy of gravity factors in a couple things. The more mass an object has, the more potential energy it has at that point. The acceleration of gravity, right? If we had a higher acceleration of gravity, we'd have a higher kinetic energy at the bottom, so that makes sense. And height. The further up I lift it, the more energy it could possibly have when it falls down. So think more kinetic energy. So potential energy is the term we use because it's not actually making use of that energy at the moment when it's just being held up here in the air. It has it, but it's sort of a stored energy. So potential energy, and you can kind of think of potential energy as being a stored energy. And then as we let go, that potential energy gets transferred to kinetic energy. And as we'll see later on, those two things actually happen to be equal as long as we're not worrying about air resistance or anything like that. That the potential energy we have up at this point was equal to kinetic energy, which is also equal to the amount of work we had to do to lift that object up. One of the main reasons we do this is because it's actually going to make problems really easy to solve. So for example, I talked about, what would be the velocity down here at this point. Well, let's just set up, we know that our potential energy gets transferred to kinetic at the bottom, so that means my potential energy at the top gets transferred to kinetic at the bottom, masses cancel out, 9.8 meters per second squared times 2 meters, 1/2 v squared, so v would be the square root of 2 times 9.8 meters per second squared times 2 meters, and whatever that equals would be our velocity. And you could almost make the case that that was even easier than using some of our kinematic equations that we could have previously used. So there's a lot of times where considering taking the systems and energy approach to solving a problem can be a very beneficial thing. Another place we could possibly store energy would be in a spring. So let's say we have a spring like this with an object attached to it. And we take our object and we push back and we compress our spring. We can store energy there, right? If we let go of the spring, then all of a sudden this object is going to go moving forward this way with some velocity, and it's going to have kinetic energy. If we take the approach where our system includes our spring, we have to include a type of energy in there because we're now no longer doing any external work. It's coming from inside the system. And so that spring potential energy has its own equation, which is 1/2 kx squared. K, in this case, represents our spring constant, right? We kind of know from our everyday experience that different springs have sort of a different amount of stretchiness to them or a different strength to them. This spring constant gives us an idea of how strong that spring is. Spring constants are measured in newtons per meter. So you can kind of look at that and say, okay, well, it's how many newtons of force that spring would provide per meter that it's compressed. And that's kind of what spring constant tells us. So stronger springs will have a really big spring constant, sometimes even in the thousands, but maybe high hundreds would be a more realistic number of newtons per meter. X is the distance that we are stretched or compressed. Notice I say stretched, right? We could stretch out a spring and then let it go and it would go flying backwards. Because this is squared, we can just call it a distance stretched or compressed rather than a displacement. because even if this were negative, when we square it, that negative goes away. So we're always going to end up with a positive value. And just like with the gravitational potential energy that we showed in the previous example, we can transfer from one type of force to one type of energy to another. So this elastic potential energy could be transferred to the kinetic energy of the motion of that box. So just kind of the same deal, right? It's just storing that energy until it's used for something. So now we want to look at how these concepts we've talked about relate to the idea of a conservative force. So let's say that we take an object and we're going to lift it from 0 meters to 2 meters. So in doing that, okay, if we take our object and we place it on the ground, right, and then we're going to lift it up to 2 meters. When that happens, I've done work on it and I've given it some amount of gravitational potential energy. And now let's try a different situation. If I go here and bring it down here and move it around and move it up here and down and over and back here to 2 meters, my potential energy that I've gained is the same as the situation as before. So my change here in potential energy of gravity was path independent. And so anything that is path independent is going to be a conservative force. Everything that we've talked about up to this point is path independent, right? If we think about our elastic potential energy, that was just how the spring was. If I take the spring and I stretch it out and I move it back and forth a bunch of times and then still into the same place, I've still stored the same amount of energy. So the amount of work that I did, which is where the force part of it comes from, the amount of work that I did was the same. And so what we find is that because the amount of work that we've done, the amount of energy we've put into the system is constant, because it's independent of path, we can come up with something that says that we have conservation of mechanical energy. In other words, mechanical energy initially in a system is equal to final mechanical energy. Well, what's mechanical energy? Kinetic energy and potential energy fall under the category of potential or of mechanical energy. So we could say kinetic energy initial plus all types of potential energy initial equal kinetic energy final plus all types of potential energy final. And we can use that to solve problems. So if we know all of our information about one place, we can use it to solve for various information about another place, maybe a height or a velocity or something like that, from plugging in details for our kinetic and potential energy at those different locations.